Calculus BC, we're in the Chapter 12, Review number 1, and we're looking at problem number 2. We're given the function f of x equals e to the negative x. And we're asked to find in part a Taylor polynomial of degree 3, centered at C1. So we're trying to find p sub 3 of x, but we're centered at a 1. So what would that look like? Well, real quickly, we could say, well, because we're centered at 1, we'd have f of 1. Then we'd have f prime of 1, x minus 1 to the 1 power all over a 1 factorial, plus a second derivative evaluated at 1. Here's x minus 1 to the second power all over a 2 factorial. And finally, we'd say, well, we'll have our third derivative evaluated at 1, and then we'd have x minus 1 to the third power all over a 3 factorial. You can see I've already done some work off to the side. I've gotten f of x equals e to the negative x. I plugged in a 1 right here. You get e to the negative 1. Take your derivative. Remember your chain rule. You'll have e to the negative x. The derivative of a negative x is just a negative 1. So you'll have negative e to the negative x. You plug in a 1 right here. You'll say f prime of 1 is negative e to the negative 1. Take your next derivative. Well, the chain rule just brings down another negative 1, so we revert back to a positive term. The second derivative is e to the negative x, and I plug in a 1, and I've got e to the negative 1. You can probably see a pattern emerging here. The third derivative, take your derivative again. The chain rule says a negative 1 comes out, and you'll have an e to the negative 1 with a negative out in front of it. Now, by the way, eventually we're going to talk about error. So go one derivative beyond, and once again, with another negative 1 coming out from the chain rule, we'll have e to the negative x. And we'll get to this in a little bit. What's super different, what's drastically different is for that extra derivative, you don't plug in where you're centered, you plug in this obscure z value. So with all this information, we can very quickly write out what we've got. F of 1 is e to the negative 1. F prime of 1 is a negative e to the negative 1. And then we have our x minus 1 right here, and that's all over a 1 factorial. The second derivative is just back to a e to the negative 1, and here's an x minus 1 squared over a 2 factorial. And then the third derivative is that negative e to the negative 1, and here we have our x minus 1 to the third over a 3 factorial. So that's all well and good. While we're at it, we might as well find the remainder R3 of x. R3 of x, we're going to say this is our error bound, our Lagrange error bound. How do we deal with it? Well, we go one step beyond where we stopped. It's the fourth derivative evaluated at z. And here we'd have x minus 1 to the fourth all over a 4 factorial. But this time, like I had said earlier, this error bound is now going to be e to the negative z, and then we have x minus 1 to the fourth all over a 4 factorial. Now for part B, as we're looking here, for part B, what they're saying is, could you approximate e to the negative 1.02. I guess what you need to remember is f of x is equal to e to the negative x. So be aware of this. This can get really tricky. What we're going to do, guys, I hope it's pretty obvious, is we're going to let x equal positive 1.02. Think about that. If you let x equal positive 1.02, that's how you get e equals negative 1.02. So what you're going to do, I'm trying to do this for the sake of of time here, just trying to do this as quickly as possible. We could plug in P3 from up here. If I were going to plug in 1.02, I'm not going to show every step doing this, but if you let x equal 1.02, evidently you would get about 0.3606. So that's the whole purpose of having a series. This could actually help you evaluate, or approximate, I should say, what a function is going to have for a certain x value. Now, the next question is, how much error do we have? And they want you to use the Lagrange error bound. They want you to show that your error is going to be less than 0.5 times 10 to the negative 4th. So in other words, you want to show that you're accurate to 3 decimal places. Well, your error is coming from R3. And, right now we're going to say this is R3, but I'm plugging in a 1.02 because that's the x value that we have. So again, this is the absolute value of e to the negative z, 1.02 minus 1 to the 4th, all over a 4 factorial. And very, very importantly, what you're going to say is z has to be between where you're centered, which is 1 here, and where you're evaluating, which is 1.02. So your error is actually going to be less than this. Your error is always less than the Lagrange error bound. That's the nice thing there. So what you're going to see is your error has to be less than, well, if I bring this e to the negative z down, let's see, I'm going to have 0.02 to the 4th up on top. That's from right here, 1.02 minus 1. We'll have e to the z coming down. And 4 factorial, well, that's 4 times 3 times 2 times 1. It's actually a 24. But remember, I want this to be as big as possible. It's like a worst case scenario. So I'm going to choose a z value to make my denominator small. And I have choices between 1 and 1.02. The smaller your denominator is, the bigger your fraction is. So I'm going to choose z equals 1. And when I do that, I'm going to see that I've got 0.02 to the 4th all over an e to the 1 times 24. Now, here's the thing, guys. We can real quickly work this out. If we turn this on and we can say, well, let's just go ahead and take 0.02 to the 4th. And then I'm going to divide by, well, I need an e. By the way, if you just need a single e, you can go second divide if you wanted to, times 4 factorial, which is 24. And let's see what we get. That's 2.452. 2.452 times 10 to the negative 9th. So we're actually accurate to 8 decimal places. And that's less than, of course, what was prescribed, 0.5 times 10 to the negative 4th. So if there was a concern that you were accurate to 3 decimal places, your error is actually way better than that. Your error is right here. So good luck. We'll pick this up again tomorrow.